Hello. Okay, first things first. In this video, you'll learn how to create a new Unity project. Let's get started. First, open your Unity Hub. Select the account icon and log in with your Unity account. If it shows your initials, you're already logged in. Select Projects and then New to open the New Project window.
At this point, you can choose from a range of different templates for your Unity project. Select the Universal 3D template for this Unity project. The Universal Render Pipeline, or URP, lets you quickly and easily create optimized graphics across a range of platforms, from mobile to high-end consoles and PCs. If this is the first time you open a project with this template, you need to download the template first by selecting the Download button to the right. In the Project Name field, call this project Rollerball. Next, in the Location field, select the destination or file path for the new project. Finally, select Create Project to make your project. It will open in the Unity.
Before you begin to create your game, you need to set up your workspace and create a new scene. In the top right of the Unity window, you will find a drop-down menu labelled Layout. A layout is a collection of stored positions of the tabs in Unity. These tutorials use the default layout, so it's easier for you to follow along. But you can change and save layouts you enjoy by using this menu. These are saved in the Unity editor settings, so you can store and use them for different projects. Now you've set a layout, you're ready to create a new scene. Scenes are ways to organise the things in your game. You can think of them as different levels.
To create a new scene in the Unity editor, in the top menu, go to File, New Scene. You will be presented with 4 template choices: Basic URP, Standard URP, Empty, and Basic Built-in. The Basic URP template contains a camera and direct light that acts as a sun. The Standard URP template contains the same but includes a preset selection of post-processing effects and a global post-processing volume. The Empty template is exactly that, empty. It contains no game objects or effects and gives you a blank slate to start from. Finally, the Basic template is set up to work with the legacy built-in renderer. For this tutorial, select the Basic URP template and then select Create.
Next, save the scene by going back to File, Save As. Now save your scene into the new folder called Scenes. Let's call the scene Minigame. In the project window, you can now see the Scenes folder, and inside that, the scene called Minigame. Now that you've set up your scene, in the next video, you'll start creating the play area for your game. Now, let's get started and create a game board or playfield. You're going to do this by using a primitive plane. Primitives are simple pieces of geometry which come bundled with the Unity editor. They can be useful for creating simple prototypes without the need of an artist. Planes are two-dimensional surfaces. In this case, you'll be using a plane as the ground for your game. All objects in your scene are game objects, including the plane. To create a plane game object, either go to the menu and select Game Object, 3D Object, Plane, or you can go to the hierarchy and use the Create menu. Next, Rename your plane game object ground. You can do this by either selecting the game object and using the Enter key to allow editing, or by the title box in the inspector. Type in the new name and press Enter or Return to confirm this change. Then, select the vertical ellipsis menu in the upper right and reset the transform component. This will place the game object at the location of 0, 0, 0 in your scene. This is known as the origin point of the world, and this is where all of the coordinates in the scene are calculated from. Cool, right? Make sure the ground game object is selected and the cursor is over your scene view. Then press F to see the entire game object in the scene view. You can also select Frame Selected in the Edit menu. In the scene, you can now see grid lines indicating a plane on the y-axis. You can use the Grid Settings menu at the top of the scene view to change the axis and opacity. Next, you'll configure the plane for your game. Now you need to change the scale of the ground plane. You can do this in 3 different ways. You can select the Scale tool using the hotkey R and simply grab the axis handle you want to change and drag the handle to rescale the plane. You can also click and drag on the title of the fields you want to change in the transform component found in the inspector. Alternatively, you can type a value directly into the fields in the inspector. You can tab between fields and hit Enter to confirm your choice. Whichever approach you take, set your X and your Z scale values to 2. Now remember, a plane has no volume, so scaling the Y-axis will have no visual changes unless you go into negative numbers. In this case, the plane, which is a single-sided object, will simply face the other direction. If you place your plane in the scene and you can't see it, check your orientation between the plane and the camera to make sure that you have the correct value of 1 in the Y-axis of scale. This plane is looking good. Now it needs something to roll on it. Now that you've created a playing field for your game, you're ready to create a player game object. For this game, that will be a Unity sphere primitive. To create the sphere, in the hierarchy, select the Create menu, and then select Sphere. Rename the sphere Player. Reset the transform to make sure it's at the origin point of the scene, 0, 0, 0. Either select Edit, Frame Selected in the top menu, or while the cursor is over the scene view, press the F key on your keyboard. This will focus the scene view camera on your new sphere game object. Do you see how the sphere is buried in the plane? This is because both game objects are in the exact same location in the scene, the origin point, or 0, 0, 0 on the X, Y and Z axis. Now you need to move the sphere up until it rests on the plane, so the player can use it as a playing field. All Unity primitive objects, cubes, spheres, capsules, have a standard size. They are either 1 by 1 by 1 or 1 by 2 by 1 Unity units of measurement. Unity units can be anything you want for your game, centimetres, inches, etc. But default convention used by most people and by the Unity lighting and physics systems is 1 unit is equal to 1 metre. If you raise the player object up by half a unit along the y-axis, it will be perfectly on top of the plane. To do this, in the inspector, find the transform component. Set the position Y value to 0.5. Great! Now that you've set this up, in the next video, you'll think about the lighting in the scene of your game. You've created the basic elements to start working on your game, but what about the lighting and visuals? If you switch from the scene view to the game view, you'll see that the player game object is lit and it casts a shadow on the plane. This is because all new Unity scenes come with the default skybox and a directional light to represent the sun. Let's tweak this value to adjust the scene a little. In the hierarchy, select the directional light and then review it in the inspector. Change the tint of the light from a yellow to a pure white. Do this by selecting the coloured selection square to bring up the colour wheel. You can use the colour picker to choose a colour. To get specific results, it's best to select the exact values. For solid white, set the RGB values to 255, 255, and 255. This is looking much better. However, the grey player sphere is difficult to see on the grey background. In the next video, you'll add some colour to the game. Okay, let's add some more contrast between the player object and the floor plane. To add colour or a texture to a model, you need to use a material. This project doesn't use any textures, but we will quickly review what's included in the URP lit material. First, let's create a new folder in our project to hold the materials. In the project window, select the Create menu and then Folder. Rename this new folder Materials. With the Materials folder selected, use the Create menu again and this time select Material. See how the material was created in the Materials folder? This is because you had the folder selected when you created the material. Rename this material Background. Next, let's change the colour of this background material. In the project window, select the background material and review the inspector. In the Surface Inputs section, the first property is Base Map. Select the Base Map's colour field to open a colour picker. Change the colour to a pale grey. You can set the RGB values of 130, 130, and 130 to get the exact shade that the example game uses. The next map represents both metallic and smoothness. As this Unity project does not use textures, you can adjust these independently. First, set the metallic to 0. Then change the smoothness to 0.25 to create a map material. To apply the material to the plane, select the material in the project window, then drag it onto the plane in the scene view. If you drag it over the player sphere, it may try to assign itself there. If it does this, don't worry, use Ctrl or Command Z to undo, and then assign it to the plane. Now the background is ready, let's create another material for the player. In the project window, select Create, Material. Name this new material Player. In the inspector, select the Base Map's colour field to open a colour picker. Set the RGB values to 0, 220, and 255, which is a nice light blue. Next, set the metallic to 0 and change the smoothness to 0.75 for a shiny finish. Then, as you did before, drag the material from the project window onto the player sphere in the scene view. Great! You've almost finished setting up for the game, But let's make one additional change and rotate the main directional light so that there is better lighting on the player. In the hierarchy, select the directional light and identify its transform component in the inspector. Change its rotation to 50, 50, and 0. This will give it a better silhouette. Now you've created a player game object and a background playfield. Awesome! In the next section of this project, you'll get started with the game functionality and write a custom script to get the sphere moving around the playfield. Now that you've created a player object and a game environment, it's time to think about how the player game object should move and behave. It needs to be able to roll around on the game area, bump into walls but stay on the ground and not fly off into space, and collide with collectible game objects to pick them up. These things require physics. To use physics, the game object needs a rigid body component. To attach this, you need to, in the hierarchy, select the player game object. Next, in the inspector, select Add Component, then search for Rigid Body and add it to the sphere. You can collapse or expand the component view by clicking on the component's title bar. Whenever you expand a component like this, it will also toggle the relevant gizmos for that component in the scene view. Okay, now that the player game object can interact with the physics system, it's time to apply some forces to it. In the next video, you'll install the input system package so you can do just that. Let's add the player input to the sphere. First, in the hierarchy, select the player game object. In the inspector, select Add Component. Then, search for and add player input. This will help you get the player movement for your game set up quickly. The player sphere still won't move just yet, but you will be able to access the information this component provides about control devices, such as the player's keyboard, using a script to control the player object's movement. In the next video, you'll get started with that script. Before you create the script to control the player object's movement, let's make a folder to organize script assets. In the project window, click on the Create menu and choose Create Folder. Rename this folder Scripts. Now you're ready to create a new C# script. You'll be using C# as the programming language, as this is what Unity supports. To create a new script, you have some choices. You can go to the top menu and select Assets, Create, to create a new C# script. You can also use the Create menu in the project window. But what might be most efficient in this case is to select the player game object in the hierarchy, and then use the Add Component button in the inspector. The Add Component menu contains the option New Script. You can select this to create and attach a new script in one step. Name the new script Player Controller. Select Create and Add, or press the Enter key to confirm your selection. Unity will create, compile, and attach the script to the selected game object, in this case, the sphere called Player. Creating a script directly on a game object creates that script asset on the root or top level of our project files, shown in the project window. To keep things organised, move the player controller asset into the scripts directory you created. Next, select the script in the project window. You'll be able to see a preview of the script asset in the inspector, but you can't edit this text. Let's open the script fully. There are two main ways to do this. You can double-click on the script asset in the project window, or you can use the Open button in the inspector when the script is selected in the project window. Each of these options will open the script in your preferred script editor. This is Visual Studio by default. Don't worry if this takes a little bit of time to load, especially if this is the first time you've opened your script editor. In the next video, you'll begin to write your first custom script to get the player sphere moving. Okay, let's get started with your first script. You'll see that there is some code already there. This is a template to make it easier to get started writing Unity scripts. A function is a way to group code under one name. There are two functions included in the script template: start and update. You can use the function name as a shorthand, or call the function instead of writing the same code every time. The code in start is called when your game starts, and the code in update is called once per frame of your game. You won't actually need the update function in this script, so remove that code for now. Before you begin writing code, let's think for a moment. What do you need to do with this script? The script needs to check every frame for player input and then apply that to the player game object every frame as movement. Where will it check for the movement? The input system has a method you can use to get the data from this input. Where will it apply the movement? There are two things you can use to apply this: update and fixed update. Update is called before rendering a frame, and this is where most of your code will go. Fixed update, on the other hand, is called just before performing any physics calculations, and this is where your physics code will go. You will be moving the ball by applying forces to its rigid body. This is physics. So you will put this part of the code in fixed update. Okay, let's get started. Because you are using the input system, you need to add its namespace to the script. Namespaces are a collection of classes and other data types which can be imported at the start of your scripts. There are already namespaces used in the template. There are lots of different namespaces. The additional one you need for this script is the input system namespace. Add a new line below the first namespace. Write using Unity engine .input system semicolon. This will enable you to access the code and functions in the input system namespace in this script. The player input component will notify the player controller script of action happening by calling functions with predefined names within your scripts. For example, to create the rollerball game, you need to be notified whenever the move action happens. The predefined function for the changes in movement controls, when pressing WASD or moving a joystick on a controller, is called onMove. In that function, the computer will read the value of the input, for example, up, down, left, or right, and then use that information to move the ball using code in the update function, which you'll write later. Let's write an onMove function. The first thing you need to do is write a function declaration, which tells the computer to create a function. Below the start function, but before the final curly brace, add a new line. Write void onMove open and closed brackets. Void means that this function won't return any values. Next, add an open curly brace, leave a line, and then add a closed curly brace. The space inside the braces is called the function body, and this is where you add instructions for the computer to complete. These instructions are specifically for the function onMove. Each function has its own set of curly braces. Okay, what's next? The player input component will be sending data of type input value to your script. So you need to add this to the function's input parameters. These are variables which will be used to store and reference data for the function. Inside the parentheses in your function call, add input value, movement value. Movement value is the name of the variable you will use within the function. Input value is the type of variable. Variables can have different data types, which means they store different types of data. The movement of the rollerball sphere will be captured in two directions, up and down and left and right. In other words, the movement value variable will capture and store the data from the x direction and the y direction of input devices. This kind of data can be stored as a vector2 variable. In the next video, you'll create that variable and then start to apply the data to the player sphere. In the last video, you wrote a declaration for the onMove function. Next, let's use the method get to get movement input data from the sphere and store it as a vector2 variable. In the space inside the onMove function, add the line vector2 movement vector equals movement value dot get open angle bracket vector2 closed angle bracket open and closed brackets semicolon. This code takes or gets the vector2 data from the movement value and stores it in a vector2 variable you are creating called movement vector. The player game object uses a rigid body and interacts with a physics engine. Next, you need to use the variable you just created to add or apply forces to the rigid body and move the player game object in the scene. To do this, your player controller script will need to access the rigid body component and add force to the player game object. First, let's create a variable to hold the reference in the script. Above the start function, add the following code: private rigid body RB semicolon. This will create a private variable of the type rigid body and call that variable RB. This will hold a reference to the rigid body you need to access. The variable is private and not public because you don't need this variable to be accessible from the inspector or from other scripts right now. Next, inside the start function, write RB equals get component, open angle bracket, rigid body, closed angle bracket, open and closed brackets, semicolon. This sets the value of the variable RB by getting a reference to the rigid body component attached to the player sphere game object. There is definitely a rigid body component attached to the game object because you added that component earlier. All of the code in the start function is called on the first frame that the script is active. This is often the very first frame of the game, so the player will be able to move the sphere straight away. Now you need to set up the fixed update function so you can call add force on the rigid body stored in the variable RB. First, create a new function called fixed update below the start function, and just like that function, the type should be void because it will perform a task and not return any values, and there should be no parameters in the parentheses. You'll learn more about the uses of the void type with functions as you continue your programming learning journey. Remember to add a set of curly braces beneath the function declaration. This is where you'll add your code. Excellent! In the next video, you'll add force to the player game object's rigid body. Next, let's start to write the code for adding force. In the function body, add the code rb.addForce. Inside open and closed brackets, type movement vector, and then end that line with a semicolon. You'll probably see in your script editor that there is an error on this line. There are two reasons for this. Firstly, the variable you are trying to use is a vector2, and you need to give this method a vector3 variable. Vector3 variables store data across 3 axes, x, y, and z. These values will determine the direction of the force you add to the ball. If you head back to the editor and look at the global gizmo, you can see the arrows also indicate this. To resolve this issue, you need to create 2 new variables for the individual input directions. Underneath the rigid body variable you created, add 2 more variables called movement x and movement y. These should be private, like the previous variable, float type, which is short for floating point, or decimal point value. These give you more precision than a whole number or integer value. You can then reference these values inside of onMove and assign these values of movement vectors x and y. In onMove, add the following 2 lines of code. Movement x equals movement vector dot x semicolon. Movement y equals movement vector dot y semicolon. Excellent! The second reason you were getting an error is because the movement vector variable was created inside of onMove. That means it's what's called non-existent in the current context, as it was inside another method. To fix this, you can combine the movement floats you just created inside of fixed update to create a vector3 variable. This will take 0 as the y value because the ball needs to move along the x and z axis in 3D space. In the fixed update function, add a new line at the top of the function and write vector3 movement equals new vector3 open brackets movement x, comma, (0.0f), comma, movement y, close brackets, and then a semicolon. The f after the value signifies that this is a float value. Next, use the new vector3 variable, movement, to add force to the rigid body of the player sphere. Revise the second line of code in fixed update to rb.addForce, open brackets, movement, close brackets, semicolon. Let's save the script and then return to the Unity editor to give it a try. Use the play button to enter play mode and test. It works! But the player is moving really slowly. Leave play mode to stop testing. In the next video, you'll adjust the script to fix this. Okay, you've almost finished setting up the player movement, but the speed isn't quite right. Let's go back to your script editor to fix that. First, let's add a speed variable to the script so that you can control the player movement from inside the inspector. Go to the start of the script where you have declared other variables. Add a public float variable called speed to the start of the script with a starting value of 0. To do this, write public float speed equals 0, semicolon. Next, back in fixed update, multiply the force you are adding to the sphere's rigid body by this strength variable. To do this, revise your line of code to rb.addForce, open brackets, movement times speed, closed brackets, semicolon. Then save your script and return to the editor. Because you made the speed variable public, you can find it in the inspector on the player controller script component. Let's try changing the variable's value to 10 to see if the speed is fast enough to improve the player experience. Enter play mode and test the revised movement. Great! This looks like a good speed for the player. And the value is now exposed, so you can adjust it easily from the Unity editor if you need to. Exit play mode, and then save your changes to the scene. Congratulations! The player can now move the sphere. In the next section of this project, you'll explore how to set up the camera for your game. So right now, the camera doesn't move and from its current position, can't see a lot. To change this, you need to tie the camera to the player game object. First, set the position of the camera. Lift it up by 10 units. Tilt it down by 45 degrees. This is a typical third-person setup, with the camera as a child of the player game object. This works well for a lot of games because the camera game object will inherit the transform changes of the player game object. When the player moves in the game, the camera will move with them. However, for this game, that setup creates a problem. When the player rotates, the camera rotates as well. Because the ball is rolling, the camera is also going to inherit this motion. Let's look at this in play mode. Hold down the up arrow to move. The camera is a child of the player's sphere, so even though the camera is not moving at all relative to the player's game object, you can see that the player game object is rotating wildly and the camera's point of view rotates with it. Okay, let's exit play mode. Let's think about how to resolve this. The player game object in your game a sphere, is rotating on all three axes, not just one. In a more typical third-person game camera setup, the camera, as a child of the player game object, will always be in a position relative to its immediate parent. This position will be the parent's position in the game, modified or offset by any value in the child's transform. In this game, that approach won't work, so let's detach the camera. The new offset value will be the difference between the player game object and the camera. To do this, you need to associate the camera with the player game object with a script rather than as a child of the game object. In the next video, you'll write that script. Okay, let's start by creating the new script to control the camera. With the main camera game object selected in the hierarchy, select Add Component in the inspector. Call your new script Camera Controller. If you use the inspector to create the script, it will be placed in the root or top level of the project folders. Move it to your scripts folder. Open the new script for editing. This script needs two variables: a public game object reference to the player game object, and a private vector3 variable to hold the offset value. Inside the first curly brace, add the following line: public game object player semicolon. This will reference the player game object's position. On a new line underneath, add another variable declaration, private vector3 offset semicolon. This will store the offset value. The offset value variable is private because you're going to set the value in the script. Now that you've declared the variable, let's calculate it. To do this, you're going to take the current transform position of the camera game object and subtract the transform position of the player game object to find the difference between the two. The start function is the best place for this code. It needs to be calculated immediately when the game starts, but it only needs to be calculated once. In the start function, on a new line after the first curly brace, let's write the equation like this: offset equals transform dot position minus player dot transform dot position semicolon. This will set offset equal to the camera transform position minus the player game object's transform position. Next, you're going to use that to set the camera game object's transform position. This needs to happen every frame, so the best place for that code is the update function. Inside the first curly brace, write transform dot position equals player dot transform dot position plus offset semicolon. Now when a player moves the sphere with controls on the keyboard, the frame before displaying the camera game object is moved into a new position aligned with the player game object before the frame is displayed. This is just like what would happen if it were a child of that object, except it's only matching the position and not the rotation of the sphere. However, update is not actually the best place for this code. It is true that update runs every frame, and in update, each frame you can track the position of the player game object and set the position of the camera. However, you don't control which order all of the update functions happen. That means that the update could run before other scripts or Unity systems that will change the player position, like the physics system. So what's the solution? Well, for follow cameras and tasks like gathering last known states, it's best to use late update. Late update runs every frame, just like update, but will run after all of the other updates are done. Add late in front of the update method to change this. Okay, brilliant. Now you know that the camera position won't be set until the player has moved for that frame. Let's save the script and return to Unity to test it out. There's one thing that you need to do before testing your changes. Create a reference to the player game object. To do that, drag the player game object from the hierarchy into the player slot in the camera controller component. Now enter play mode to test what you've done. The camera follows the rolling ball without rotating, even as the ball goes over the edge. Excellent! Remember to exit play mode when you've finished testing and save your Unity project. Now that you've set up the camera, in the next section of this project, you'll configure the basic play area for the game. Okay, let's set up the playfield. The playfield for your game will be very simple. You will place walls around the edges to keep the player game object from falling off. And you'll create and place a set of collectible objects for the player to pick up. First, let's get organised. In the hierarchy, create a new empty game object. Reset its transform and then rename it Walls. This will be the parent game object for all of the wall game objects. Now you can build some walls. Let's start by creating a new cube to be the first wall. In the hierarchy, select Create, 3D Object, Cube. Rename the cube game object West Wall. In the inspector, right-click the transform component title and select Reset. This resets the component to its default values. Now drag the West Wall game object onto the Walls game object and release. This makes West Wall the child of Walls. Let's focus the scene view camera to the West Wall object. To do this, press the F key while the cursor is over the scene view, or select Edit, Frame Selected. Next, you need to change the size of the cube to fit one side of the play area. In the inspector, change the cube's transform scale X value to 0.5, Y value to 2, and Z value to 20.5. You can push the wall into place using the Translate tool, or you could enter a transform position value in the inspector. Let's use the inspector. Set the transform's position X value to -10. This places the wall neatly to the edge of the play area. Now just one more thing. Let's create a new material to change the colour of the wall. In the Project window, go to the Materials folder and select Create, Material. Rename this new material Walls. In the inspector, select the base map's colour field to open a colour picker. Set the RGB values to 79, 79, and 79. Next, set the metallic to 0 and change the smoothness to 0.25 for a matte finish. Then, drag the material from the project window onto west wall in the scene view. Great! Now you've done one wall. In the next video, you'll complete the play area. To create the next wall, you could start with another new cube, but then you'd have to rescale the new cube before placing it. Your first wall is already a perfect size. Right-click the West Wall game object and select Duplicate. Rename the new game object East Wall. To place the wall, just remove the negative sign on the position X value of the transform component. Then it will move into place on the east side of your game area. Now, let's duplicate the east wall and rename the duplicate North Wall. Reset the north wall's position X value to 0 so it moves to the centre of the play area. You now have two choices. You can either rotate the wall by 90 degrees around the y-axis, or, as this is a cuboid, you can scale the wall using 20.5 in the x-axis and 0.5 in the z-axis scale values. Now the game object is scaled correctly for its orientation as the north wall. Awesome! You can drag the wall into place by hand or set the north wall's transform z-axis position to 10 to place it. Next, duplicate north wall and rename it south wall. Set the transform z-axis position to -10 and it will move into place too. First, save your changes. Then let's enter play mode and test. Fantastic! The walls are exactly where they need to be and working properly as boundaries of the play area. Remember, it's important to test early and often to catch errors as soon as possible. Let's exit play mode now. The walls are colliding with the player sphere because cube primitives come with a box collider component by default. This interacts with game objects with rigid body and collider components. If you're encountering issues with wall collisions, you may have accidentally enabled the isTrigger property on the collider component. This means the collider will be used to trigger events via script and won't be used for collisions. To fix this, disable the isTrigger property checkbox. You've now completed the playing area for your rollerball game. In the next part of this project, you'll create the pickup objects for the player to collect. Let's get started creating objects for the player to collect. In the hierarchy, select Add, 3D Object, Cube. Rename the cube Pickup. In the Transform component, use the vertical ellipsis to reset the game object's transform to origin. Press F to focus the scene view camera on the Pickup cube. The player game object is currently overlapping the new cube, so select the Move tool and drag Pickup out of the way while you work on its functionality. The cube is currently buried in the plane, just like the player sphere was when you started this project. Remember that? The cube is also a regular shape, 1 by 1 by 1. So let's lift it up by half a unit, so that it rests on top of the plane. In the transform component for the pickup game object, set the position Y value to 0.5. This cube will be the collectible object in the game. To be effective, it needs to attract the attention of the player. So let's make the cube visually interesting. How about making it smaller? In the transform component, set each of the scale axis values to 0.5. This will give it the effect of floating above the play area. That will help identify this object as special. But perhaps that's not enough. Let's tilt it too. Set each of the rotation axis values to 45. The cube also needs to stand out more against the background walls and the player game object. Let's change its colour by creating another material. In the project window, find and select your first material, background. In the top menu, go to Edit, Duplicate. Rename the new material Pickup. With the Pickup material still selected in the project window, use the Colour Picker in the inspector to change its base map colour property. Let's make it yellow and use the RGB values 255, 200 and 0. Now you can change the colour of the pickup game object by changing its material on the Mesh Renderer component, or by dragging the material from the project window onto the cube in the scene view. Now it's starting to look more like a pickup, but it's still very static. One thing that attracts attention of a user is movement. In the next video, you'll write a script to rotate the cube. Okay, let's get that cube rotating. As you've done before, select the pickup game object in the hierarchy, and then select Add Component, then New Script in the inspector. Call the new script Rotator. Then select Create and Add to confirm. In the project window, move the Rotator script to your Scripts folder to keep things organised. And then open the script to edit it. Once it's opened in your script editor, remove the Start function from the template. You won't be using forces to rotate the cube, so you can use Update rather than using the Fixed Update function, so the rest is fine. Now, before you begin, let's think for a moment about what this script needs to do. It needs to make the pickup game object spin while the game is active. You have already set up the pickup game object's transform rotation property to 45, 45, and 45 for the X, Y, and Z axes. But these values don't change by themselves, and for the cube to spin, these values need to change every frame. To do this, you need to write a script that rotates the game object's transform. There are two main ways to affect the transform of a game object. These are translate and rotate. Translate moves the game object by its transform. Rotate rotates the game object by its transform. It has two possible initial parameters. One using a vector3 variable, and the other using 3 float values for X, Y, and Z. The simplest option is the vector3 parameter, which is all that's needed for this game. After the opening curly brace of the update function, add the following line of code. Transform dot rotate, open brackets, new vector3, open brackets again, 15, 30, 45, then 2 closed brackets, semicolon. Make sure that transform is a lowercase t, because you're referring to the component, not the variable type. This action also needs to be smooth and frame rate independent. To do this, multiply the vector 3 value by time.delta time before the closing parentheses. Delta time is perfect for ensuring actions happen smoothly, because delta time is a float representing the difference in seconds since the last frame update occurred. It will dynamically change its value based on the length of a frame. Okay, that's all you need. Save this script and return to Unity. Let's enter play mode and test the script. Excellent! The pickup game object rotates. Exit play mode when you're done testing. Remember to save your Unity project frequently. Now's a great time to do that. Now you've made a beautifully rotating collective object, but there's only one. In the next video, you'll learn how to turn the pickup game object into a prefab and add lots of collectible objects to the play area. Now you've created one rotating pickup collectible, it's time to place them around the play area. There's one vital step needed to do this. You need to make the pickup game object into a prefab. A prefab is an asset that contains a template or a blueprint of a game object or game object's family. Once a game object is turned into a prefab, you can use the prefab in any scene in your current project. By turning the pickup game object into a prefab, you will be able to make changes to a single instance of the prefab or to the prefab asset itself. And all of the pickup game objects in the game will be updated with those changes. So let's get started. First, go to the project window and check that you're at the root, or top level of the project. Make sure that no other item or directory is highlighted. Select Create, Folder, and rename this folder Prefabs. Now, select the pickup game object in the hierarchy and drag it into the Prefabs folder. When you drag an item from the hierarchy into the project window, Unity creates a new prefab asset containing a template or a blueprint of the game object or game object family. Your game object will turn blue in the hierarchy when it becomes a prefab instance. Select the arrow to the right of the pickup prefab in the hierarchy to open the prefab edit mode. From this mode, you can use the arrow at the top of the hierarchy to return to a normal scene view. Now you've turned the pickup game object into a prefab. In the next video, you'll instantiate it around the play area for your players to collect. Okay, let's fill the play area with rotating pickup objects. Before you start, let's keep things organised. In the hierarchy, create a new game object and call it Pickup Parent. In the inspector, right-click the transform component title and select Reset to reset Pickup Parent to origin. Then, in the hierarchy, drag the pickup game object onto Pickup Parent. Next, make sure that you have the child pickup game object selected in the hierarchy, not the parent. Select the gizmo in the upper right of the scene view to switch to a top-down view. Now, use your scroll wheel to zoom out a little so you can see the entire play area. Okay, let's start placing pickup objects. Move the first pickup game object somewhere you like. Next, let's duplicate the game object. Make sure it's selected and then go to Edit, Duplicate. You can use the hotkeys Ctrl-D for Windows or Command-D for macOS. Now place the second instance of the prefab. Using the hotkeys, create some more pickup game objects and place them around the play area. About 12 is a good number for this game. To make this easier, you can move parallel to the ground or XZ plane by selecting the XZ plane at the center of the gizmo. Okay, that's 12. At the moment, the collectible objects are present in the game, but the player can't actually collect them. That functionality is the next thing you're going to add. Okay, what's next? Well, your players need to be able to collect the pickup game objects when the player game object collides with them. For this to happen, the game needs to detect the collisions between the player game object and the pickup game objects and use this information to trigger a new behaviour. It's really important to test the collisions carefully. The pickup objects, the player's sphere, the ground plane, and the walls all have colliders. Without testing, the player might be able to collect and disable the wrong objects in the scene, for example, the ground plane. Let's get started. In the project window, go to the Scripts folder and open the Player Controller script for editing. Before you begin writing the script, let's think about what the code needs to do. It needs to detect and test collisions on the player's sphere collider. To do this, you're going to use the function onTriggerEnter. Imagine that you're playing a platform game, and you jump up to collect a perfect arch of coins, but bounce off every first one and fall back to the ground. That's not very elegant. The onTrigger function will detect the contact between the player game object and the pickup game objects without actually creating a physical collision. Let's start with the function declaration and parameters. Beneath the fixed update function, write void onTriggerEnter open brackets collider other closed brackets. Next, remember to add a set of curly braces to contain the function body. onTriggerEnter will be called by Unity when the player game object first touches a trigger collider. It will be given a reference to the trigger collider that has been touched. This is the collider called Other. This reference gives you a way to identify the colliders that the sphere hits. You could destroy the game object that the trigger collider is attached to. However, in case you want to add additional functionality to the collectible objects later on, in this project, you'll only deactivate the game object rather than destroy it. So how can you deactivate the correct object, and in this case, the pickup game objects, using a script? Let's start to write the first line of code inside the function body for onTriggerEnter. You can address the other collider's GameObject through other.GameObject. To disable it, you need to use the method setActive. This method accepts a Boolean value inside the parentheses, that is, true or false. Use false to disable the GameObject. The full line should be other.GameObject.setActive open brackets false closed brackets semicolon. This code will disable GameObjects correctly, but you don't have a way to filter which GameObjects the sphere can disable. In the next video, you'll use the Unity tag system to do just that. Now, you've written code to deactivate GameObjects that the player GameObject collides with. But this should only apply to the pickup GameObjects. The ground or walls disappearing would not be good. To do this, you're going to use the built-in Unity tag system. Tags allow you to identify a GameObject by comparing the tag value to a string. The first thing we need to do is set up the tag value for the pickup object back in the Unity editor. In the project window, go to the prefabs folder and select the pickup prefab. You can also use the arrow next to one of the prefab instances in the hierarchy. This opens prefab edit mode. In the tag list at the top of the inspector, there's a few pre-made tags, but there's nothing called pickup. Select Add Tag. This brings up the Tags and Layers panel with a list that's currently empty. To create a new custom tag, select the Add button to add a new row to the tag list. In the new empty element, which will be tag 0, type pickup. This is case sensitive, so be careful. It needs to be exactly the same string that you use in the script. You can close the Tags and Layers panel when you're done. Now you need to apply that tag to the prefab asset. Select the tag drop-down again. You should see that your new tag is now available in the list. Select this tag from the list. The asset is now tagged pickup. Use the arrow to leave prefab edit mode. And with the power of prefab, all the instances are also now tagged pickup as well. Great! Save your changes in the Unity editor before you return to the script. In the next video, you'll use this tag to make sure the sphere can only disable GameObjects with the pickup tag. Now that you've created a pickup tag, you can use it to make sure the sphere only disables the correct GameObject. Let's do that using an if statement. This means that if a certain condition is met, the script will behave in a specified way. To create the if statement, you're going to use compare tag. Compare tag can compare the tag of any GameObject to a string value. At the top of the function body for onTriggerEnter, write if open bracket, other dot game object dot compare tag, open brackets, and in quotation marks write pickup, and then close that statement with 2 closed brackets. This is the if statement. Be careful here. Comparison is case sensitive. Make sure to write the tag exactly as you did it in the Unity editor. Next, add a set of curly braces and cut and paste the line that reads other dot game object dot set active, open brackets, false, close brackets, semicolon. Now this code will be called every time the sphere game object touches a trigger collider. It will receive a reference for the collider that the sphere has hit and then check its tag. If it is a collectible object, the script will call setActiveFalse, which will deactivate the game object. Let's save this script and then return to the editor and enter play mode to test the game. So the tag is set correctly, but the sphere is still bouncing off the pickup cubes, just like we were bouncing off the walls. In the next video, you'll explore why this is happening and fix it. So, you created tags and used them to differentiate the pickup game objects. But when you tested the game, the sphere didn't disable them on collision. This is because the pickup game objects are still using normal colliders and not triggers. Remember, colliders will stop physics objects from overlapping with them, which is perfect for a wall, for example, but triggers will just notify you if something is overlapping without stopping it. You can fix this issue by making the colliders into triggers or trigger colliders. When you turn a collider into a trigger, you can detect the contact with the trigger through on-trigger event messages. When a collider is a trigger, you can do some clever things. You could place a trigger in the middle of a doorway in, say, an adventure game. When the player enters the trigger, the minimap could update and a message could be displayed to tell them you have discovered a new room. Or, every time the player walks around a particular corner, spiders might drop from the ceiling because they have walked through a trigger. You have already used on-trigger enter in your code, rather than on-collision enter. Now you just need to make sure the collider is set to be a trigger. Let's get started. First, check that you're not in play mode. Changes made in this mode won't be saved. Next, go to the prefabs folder in the project window and select the pickup prefab. Now find its box collider component in the inspector and enable the Is Trigger checkbox. Now, through the power of prefabs, all the pickup game objects have trigger colliders. Let's save the scene and enter play mode to test it. OK, as the player's sphere enters the trigger, the pickup game objects disappear. Excellent! Everything looks great, so you can exit play mode. You're almost done on this section of the project. There's one last tweak to make in the next video. There's one more tweak you can make to the collectible cubes, adding a rigid body component. Any game object with a collider and a rigid body is considered dynamic, which means Unity won't treat it as static or stationary. You don't want the pickup game object to be considered static, as it will take Unity longer each frame to calculate the physics, and it will do this each frame because the cubes are rotating. The solution is to add a rigid body component to the pickup objects. In the project window, go to the prefabs folder and select the Pickup Prefab. In the inspector, select Add Component and add a rigid body. Save your changes, then test in play mode. And, the cubes all fall through the floor. The force of gravity is pulling them down, and as they are triggers, they don't collide with the floor. If you find the rigid body component in the inspector, you'll see that you could just disable the Use Gravity checkbox, which could prevent the cubes from being pulled downwards. However, this is only a partial solution. If you do this, even though the cubes would not respond to gravity, they would still respond to physics forces. There is a better solution. Enable is kinematic. This sets the rigid body component as a kinematic rigid body. A kinematic rigid body will not react to physics forces, and it can be animated and moved by its transform. This is great for everything from objects with colliders, like elevators and moving platforms, to objects with triggers, like your collectible cubes that need to be animated or moved by their transform. Let's save the scene again and enter play mode to test. Now the cubes do what they did before, but more efficiently. Excellent! So, to recap, static colliders shouldn't move, like walls and floors. Dynamic colliders can move and have a rigid body attached. Standard rigid bodies are moved using physics forces. Kinematic rigid bodies are moved using their transform. In the next section of this project, you'll count the collected objects and make a simple UI to display the player's score and messages. In this section of the project, you'll explore counting the collected cubes, displaying text, and ending the game with a message. First things first, the collectibles. To count these, you'll need a tool to store the value of the counted collectibles, and another to add the value as we collect and count them. Let's add this functionality to the player controller script. Select the player game object in the hierarchy and open the player controller script for editing. First, let's declare a private variable to hold the count. This should be an integer variable, written as int, because the count will be a whole number. The player won't be collecting partial objects. Underneath the rigid body variable declaration, write private int count, semicolon. Naming the variable count makes it easier to understand its role in context. The game needs to start with a count value of 0. Each time the player picks up a new cube, it then needs to increase by 1. As the count variable is private, you won't be able to set its initial value in the inspector. You'll need to do that in this script. There are several ways you can set the starting value of count, but for this game, let's do it in the start function. In start, write count equals 0 to set the initial count value to 0, followed by a semicolon. Next, you need to increase the count variable when the player collects a cube. These cubes are collected or disabled to make them disappear in the on trigger if the other game object has the tag pickup. That means the on trigger enter function is where you need to add the counting code. After setting the other game object's active state to false, add another line of code to add 1 to the variable count, then save it back to that same variable. This is a basic form of incrementing a value. To do this, write count equals count plus 1, then add a semicolon. There are other ways to add, count up, or increment the value when coding for Unity, but this one is the easiest to explain visually. Now save this script and return to the Unity editor. In the next video, you'll create and configure a UI text element so that you can display the incremental count value to the player. Now you can store and increment the player's collectible cube count, but there's currently no way to display it. To do this, you're going to use two systems built into Unity: the User Interface or UI system and TextMesh Pro. Let's get started by creating a new TextMesh Pro text element in the Unity editor. First, in the hierarchy, select the Add button and go to UI, Text, TextMesh Pro. A dialog window will open to install TextMesh Pro Essentials. Select Import TMP Essentials. These resources will be added to a new folder at the root of your Unity project. Close the window when you're done. Now you'll see that some new things have appeared in the hierarchy. Let's review them. There's Text, TMP, the UI text element. There's also a parent game object for that text element called Canvas, and another game object called Event System. These game objects are all required by the UI toolset. The single most important thing to know about these additional items is that all UI elements must be the child of a canvas to behave correctly. Rename the text element game object Count Text. Now, select the canvas and press the F key to see the entire game object in the scene view. Then, select the 2D toggle at the top of the scene view to change to 2D view. The default text color is white. The size and alignment are good, but let's add some placeholder text. In the text field, at the top of the component, add Count Text as your placeholder. Now, to avoid getting in the player's way, it makes sense to display the count in the upper left of the screen when the game is playing. It's currently in the center of the scene. This is because the text element is anchored to the center of its parent, which is the canvas. It is worth noting here that the transform component on the UI object is different from the other game objects in Unity. For UI objects, the standard transform has been replaced with a rect transform, which takes into account many specialized features necessary for a versatile UI system, including anchoring and positioning. One of the easiest ways to move the count text element into the upper left of the screen is to anchor it to the upper left corner of the canvas, rather than to its center. To do this, select the icon at the top of the Rect Transform component displaying the current anchor preset. This will open the Anchors and Presets menu. Hold Shift and Alt or Option and select the top left anchor point. Holding those keys will set the pivot and position for the count text based on the new anchor. And now the UI text is up in that corner. Great! It does look a little cramped though. Let's add some space between the text and the edge of the screen. The simplest way to do this is to change the Rect Transform component's pos x value to 10 and pos y value to -10. Now that looks better. In the next video, you'll make the UI text element display the actual count value for the game. Now that you've created a UI text element to display the count, let's connect this to the player controller script to get it working. In the project window, go to the scripts folder and open the player controller script in your script editor. Before you can code anything related to the TextMesh Pro element, you need to add information about it to the script. The details about the UI toolset are held in what's called a namespace. You imported another namespace earlier in this project to access the Unity input system. To import the namespace for TextMesh Pro into this script, create a new line underneath the input system namespace and write using tmpro semicolon. With this imported, you can now write code relating to the element. Next, underneath the public variable called speed, create a new public TextMesh Pro variable using the type TextMesh Pro UGUI called countText. Make sure to add the semicolon at the end of the variable declaration. This variable will hold a reference to the UI text component on the countText game object. Now, you need to set the starting value of the UI text property and get it to change as the count value changes throughout the game. It's worth creating a new function for that to avoid duplicating lines of code. Underneath the onMove function's closing curly brace, leave a space and write void set count text, open and closed brackets. Add a set of curly braces beneath this to contain the function body. You can now set the count text equal to the int or whole number value of count. To do this, write countText.text equals quotation mark count colon quotation mark plus count dot toString open and closed brackets semicolon. This function must be called after the line of code setting the count variable's value within the start function, because count needs to have a value that can be used to set the UI text. Let's add a call to set count text to the end of the start function. Write set count text, open and closed brackets, semicolon. The UI component's text also needs to update every time the count variable is incremented after the player collects a cube. Inside the if statement for the on-trigger enter, call the setCountText function again using the same instruction. setCountText, open and closed brackets, semicolon. Excellent! Save your changes and switch back to the Unity editor. Now, the player controller script component has a new text property. Select the player game object in the hierarchy, then drag and drop the countText game object onto the slot to reference the UI text element. Unity will find the TextMesh Pro UGUI component on the game object and correctly associate that reference. Now let's save, enter play mode and test. Great! Now the count is displayed and increments correctly as the player collects cubes. Remember to exit play mode when you're done testing. Your rollerball game is almost complete. In the next video, you'll add a little more UI text to your game to create a game end message for the player. To finish up your UI work, let's add a simple message for the player when they've collected all the cubes. First, create another UI text object. In the hierarchy, select the Add button and go to UI, Text, TextMesh Pro. Just like before, the new UI element has been created as a child of a Canvas game object. Rename the UI game object WinText. In the inspector, find the vertex color property in the TextMesh Pro component and use the color picker to set this to black. Let's also make this text a little smaller. Set the font size to 32. You could also make it bold using the B button in the font style field. In the text field, add "You win." Lastly, let's adjust the alignment of the text to the center of the player's screen, but raised above the middle on the vertical axis, so you won't cover the player's sphere. By default, the UI text element is anchored to the center of the canvas, so you just need to raise it and move it across. In the rect transform component, set the pos x value to about 0 and the pos y to 130. Let's also set the alignment to center. Then, save the scene and switch back to your script editor. Now you need to add a reference for this UI text to the player controller script. But as you only need to disable and enable the text, you can just create a reference to the game object. At the top of the script, with the other variable, create a new public variable of the type GameObject and call it WinTextObject. Remember to add a semicolon at the end of the declaration. Next, let's set the starting state for the object to be disabled. This text should only display when the player has completed the game. Because it's a starting state, add the code disabling the UI text to the start function. Write an instruction using the same method that you used to disable the collectible cube game objects on collision. WinTextObject dot set active open brackets false closed brackets semicolon. You also need to set when the UI text game object will be activated. Let's add this to the setCountText function. Underneath the instruction setting the count value UI text, write if, open brackets, count, greater than, equals 12, closed brackets. Then add curly braces to contain the code. An important note: if you add a different number of collectible cubes to the game, perhaps a few more than 12 or a few less, your if conditional statement must reference that number. Otherwise, the game end text may display too early or might not display at all. Inside the curly braces, set the WinText object to active. WinText object dot set active, open brackets, true, closed brackets, semicolon. Then save your script and return to the Unity editor. Just like before, the player controller component has a new UI text property. Select the player game object in the hierarchy, then drag the WinText game object from the hierarchy into the slot. Save the scene and enter play mode to test your changes. So, the player can collect all the cubes, see the count go up, and then receive a win message when they've collected them all. Awesome! In the final section of this project, you'll create a build of your game and deploy it using a standalone player. You're almost finished.
The game will be a lot more exciting if there's some risk involved. In this tutorial, you'll create an enemy game object that will chase the player. Let's start by creating a new empty game object. Right-click in the hierarchy and select Create Empty. Rename it to Enemy. Reset the transform of the enemy game object to position it at 0, 0, 0. You can do this by selecting the enemy game object in the hierarchy and then click on the gear icon in the inspector and choose Reset. Inside the enemy game object, you will create a cube to represent the enemy's body. Right-click on the enemy game object, select 3D object and choose Cube. Name the cube Enemy Body. Adjust the scale of the enemy body to make it a bit taller. In the inspector, locate the scale values and set them to 0.5, 1 and 0.5. Set the position of the enemy body to 0, 0.5, 0 to position it above the ground. Great! Now let's create a material for our enemy and assign it to the enemy body cube. Open the Assets folder in the project window and navigate to Materials. If there isn't a Materials folder, you can create one by right-clicking in the project window, selecting Create, and then choosing Folder. Name the folder Materials. Right-click inside the Materials folder, select Create, and then select Material. Rename the material to Enemy. With the enemy material selected, in the inspector, locate the base map colour property and set it to whatever colour you want for your enemy. Now simply drag and drop the enemy material onto the enemy body cube in the scene view or hierarchy. You now have an enemy game object in the game, but it won't move around yet. We'll get started on that next. The Unity Nav Mesh is a tool for implementing efficient pathfinding, enabling AI agents to navigate complex environments, avoiding obstacles along the way. In this tutorial, you'll set up the nav mesh for your scene. Start by selecting the scene geometry where you want the enemy to be able to walk. In this case, you'll select the ground game object. With the ground selected, in the inspector, select Add Component. In the Add Component menu, search for and select Nav Mesh Surface. The Nav Mesh Surface component represents the walkable area for a Nav Mesh agent. Select Bake in the Nav Mesh Surface component. This will initiate the process of generating the nav mesh based on the scene geometry and the specified settings. After the baking process is complete, the nav mesh will be displayed in the scene as a blue overlay. But there's a problem. The pickups are currently being factored into the nav mesh, with the enemy either going around them or walking over them. For this game, we want the enemy to ignore these pickup objects entirely. In the inspector, in the Nav Mesh Surface component settings, locate the Object Collection section. Set the Collection Objects drop-down to Current Object Hierarchy. This ensures that the nav mesh only takes the ground object and any of its child objects into consideration, and therefore ignores the pickup objects when baking the mesh. Select the Bake button again. The pickup collectibles are now ignored in the nav mesh. You now have the nav mesh set up for your scene. The enemy won't navigate on it yet though, you'll do that next. In this section, you will set up the enemy with the necessary components to chase the player around the scene. First, let's make the enemy a nav mesh agent. This will allow the enemy to detect the nav meshes in the scene, calculate movement paths, and navigate around obstacles. Select the enemy game object in the hierarchy. Search for and add a nav mesh agent component. The nav mesh agent component provides various properties that can be adjusted to change the movement of your enemy. Find the speed property under the steering heading and set it to something around 2.5. The enemy still won't move around the scene because it doesn't know where to go yet. You need to give it a target in a new script. Select the enemy game object in the hierarchy. In the Add Component menu, search for and select New Script. Name the script Enemy Movement and press Enter. This will create a new script component attached to the enemy game object. To keep things organised, let's move the script into the Scripts folder. Open the enemy movement script by double-clicking it in the Scripts folder or in the Script component in the inspector. In this script, you'll be referencing properties of the AI navigation package. Add using Unity Engine.ai to the top of the script, right under the Using Unity Engine line. This gives you access to some nav mesh related functions and the properties you'll need. You'll also need to add a reference to the player game object, since the player will be the enemy's target. Add a new line and declare a variable named player of type transform. This will allow us to access the player's position. Next, we'll need to reference the NavMesh agent component on the enemy game object. Declare a private variable named NavMesh agent of type NavMesh agent. In the start function, add this line between the curly brackets. This line of code will find and assign the navmesh agent component to the navmesh agent variable. Moving on, in the update function, every frame, we will check if the player exists with a null check. If the player is found, the enemy should move towards it. You can do that by setting the navmesh agent's destination to the player's position. The exclamation mark and equal sign makes a not condition. The line therefore means if the player does not equal null, or if the player does exist, continue with the function. Remember to add a semicolon at the end of each line. Save the script and return to the Unity editor. Select the enemy game object in the hierarchy and then drag the player game object into the player slot of the enemy movement script component in the inspector. This will assign the player game object to the player variable in the script so that the enemy knows the player is its target. Save the scene and run the game. You should now see the enemy move around and follow the player game object. You have successfully implemented enemy movement in your game. Next, you'll create a few obstacle objects the player can hide behind. In this section, you'll create static obstacles for your game and configure them to work with the navmesh obstacle avoidance feature. This will make the game much more challenging and interesting. Let's start by creating the obstacle game objects. Right-click in the hierarchy, navigate to 3D objects and choose one of the standard 3D objects to create an obstacle. Repeat this step to create additional obstacles with different shapes and ramps. Feel free to move, rotate and scale the obstacles to customize their appearance. Make sure to turn at least one object into a ramp to test your enemy's slope climbing abilities. To ensure that the navmesh surface takes the obstacles into account when baking, we need to make them child objects of the ground game object. Remember that in this case, the navmesh surface object collection parameter is set to consider only the child objects of the ground game object. In the hierarchy, drag each obstacle game object onto the ground game object to make them child game objects. Once you have made all the obstacles child objects of the ground game object, it's time to rebake the navmesh to include the new obstacles. Select the ground game object and click on the Bake button in the navmesh surface component to regenerate the navmesh with the updated obstacle configuration. You should now see the area around the obstacles carved out of the blue navmesh surface overlay in the scene. In the navmesh surface component, from the Agent Type dropdown, select Open Agent Settings. In this window, you can adjust the properties of your navmesh agents. Increasing the step height will allow the agent to hop up onto higher surfaces. Increasing the max slope will allow the agent to climb up steeper hills. Adjust these settings, rebake, and test the effect they have on your scene. You have successfully created static obstacles for your enemy. Next, you'll implement dynamic obstacles that will update the baked navmesh live during the game. Nav meshes are typically static once they are baked, but in some cases you want dynamic objects in the scene to update the nav mesh at runtime when they change their positions. The nav mesh obstacle component will allow you to do this. Let's start by creating a cube with a new material to serve as our dynamic nav mesh obstacle. In the Game Object menu, navigate to 3D Object and select Cube. Rename the cube to Dynamic Box. Next, create a new material and name it Dynamic Obstacle. Give it a colour of your choice and assign this material to the Dynamic Box object. To give the box physics properties so the player can push it around the scene, you'll need to add a rigid body component to it. Select the Dynamic Box cube in the hierarchy, search for and select the rigid body component. In the rigid body component, reduce the mass to make it more lightweight. You can run the game and test different mass values until you find the one you like. Test the scene and notice that the enemy goes straight through the dynamic box. This is because the nav mesh is not aware of the obstacle yet. To make the nav mesh aware of the dynamic obstacle, select the Dynamic Box cube, then search for and add the nav mesh obstacle component. This component allows a moving obstacle to affect the nav mesh during the game. By default, the nav mesh obstacle component will make the AI path find around the obstacle without carving a hole in the nav mesh around it. However, enabling the carve option creates a larger hole in the nav mesh around the object, which ensures that the obstacle doesn't get too close and potentially cause the AI to get stuck. Enable the carve option in the nav mesh obstacle component. To create multiple instances of the dynamic obstacle, let's make the Dynamic Box cube into a prefab. With the dynamic box selected in the hierarchy, drag it from the hierarchy into the prefabs folder in the project window. This will create a prefab of the Dynamic Box cube. Now you can duplicate and scatter the prefab instances around the play area as desired. You've successfully created dynamic obstacles that the AI knows how to avoid, and the player can interact with them during runtime. Next, let's update the winning and losing conditions to take the new game dynamics into consideration. In this section, you'll set up the win and lose conditions for your game. When the enemy catches the player, the game should end and say, "You lose." When the player collects all the collectibles, the enemy should stop chasing the player. Let's start by opening the player controller script in your preferred scripting editor. Add a new onCollisionEnter function after the update function. When a collision is detected, you need to check if the collision object was the enemy. This can be done with the compare tag property. If the tag is enemy, the player game object should be destroyed. The win text object should also be activated and then updated to display the text "You lose." Save the script and return to the editor. Now you need to make sure that the enemy game object has the correct tag. Select the enemy body game object in the hierarchy. In the inspector, locate the tag drop-down and select Create New Tag. Click the plus icon to create a new tag and name it Enemy. Make sure the capitalization matches what you wrote in your code. Save the new tag. In the inspector, select the enemy body game object again and set its tag to the newly created enemy tag. This step is crucial and should be set specifically on the enemy body. Run the game to test. Now, when the enemy collides with the player game object is destroyed and the updated text displays "You lose." Finally, you want the enemy to stop chasing the player when the winning condition is achieved. Back in the player controller script, you already have a function named setCountText that runs when the winning condition is met. All you need to do now is destroy the enemy game object as well. By adding this line in the setCountText function, you can destroy the enemy game object. Notice that you are once again using the enemy tag to find the correct object to destroy. Tags are a powerful way to find specific objects in a scene. Save the script, return to the editor, and run the game to test the win condition. When you collect all the coins, the enemy is destroyed. Congratulations! You have successfully set up the win and lose conditions for your game. You now have a simple, complete game loop.